Chapter 13, Air Pollution. The sources of primary pollutants. There are two categories. There are natural pollutants and human pollutants, causes that are created by humans. So, of the natural pollutants, there are volcanoes, breaking seas, pollens, terpenes, wildflowers that make pollen, wildfires, creating ash and smoke in the air, blowing dust, and bacteria and viruses. Now, these last three, wildflowers, dust, and bacteria and viruses, are accentuated by humans. They're made worse by humans. For example, wildfires are natural, but they can also be human caused. If a human starts a fire and it spreads and becomes a wildfire, that is caused by a human. Versus a lightning strike, which would be natural, or a volcano causing a fire, which would be natural. They can also be caused by humans, or made worse by humans. Now, in the created by humans category, we have combustion processes, chemical processes, nuclear or atomic processes, roasting, heating, and refining processes, mining, quarrying, and farming. The next slide has some pictures of different forms of pollution and an example of a satellite image where you can actually see the pollution on a satellite image. There's also a picture of it's an industry, what are they called? Smokestacks, I think, where it's billowing out fumes and smoke and stuff. Similar to what they have over in Chemical Valley. And it's got a picture of wildfires, which cause like smoke, ash, and even burning of chemicals like plastic or whatever it is that catches on fire besides just wood smoke that releases chemicals into the air. Those would also be pollutants. Sources and types of air pollution. So we've got a little diagram here where carbon monoxide is the greatest pollutant on this chart at over half, 55.1 million tons. Nitrogen oxides, which are 12.3 million tons. Volatile organics, which are 14.2 million tons. Sulfur dioxide, which is 4.9 million tons. And particulates, which are 3.6 million tons. It says here, percentages are calculated on the basis of weight. 6 major air pollutants. So the 6 major air pollutants monitored by the EPA include particulate matter, which is PM, sulfur dioxide, which is SO, nitrogen oxides, which are NO, carbon monoxide, which is CO, lead, which is PB, and ground level ozone. Because if you remember from the previous chapters, Ozone in the sky is alright, it's good, we need that up there to filter out the sun's rays, but when it's down here in the troposphere, it's not so great. And there's a picture here of how small different types of pollutants can be compared to a human hair. And the human hair is massive in comparison to particulate matter, which is very, very tiny. And it's very tiny in comparison to a grain of sand. This one particulate matter in the picture looks just like a little dot on the page. Carbon monoxide. Although carbon monoxide output varies seasonally, the trend has shown a steady decline from 2000 to 2014. Lead and smog. Lead is very dangerous because it accumulates in the blood, bones, and soft tissues. It can impair the functioning of many organs. Smog is air pollution in urban and industrial areas. Ozone and photochemical smog. Ozone, in addition to various nitrogen-based irritants, is a major component of photochemical smog. There is a little picture here of all of the different factors of photochemical smog, but I'm going to skip that for the moment. Volcanic smog, or VOG, is it's actually a natural form of smog. It's created when sulfur dioxide from a volcano combines with oxygen and water vapor in the atmosphere. And there's a picture here from NASA's Terra satellite where on December 9th, 2009, the Kilauea volcano on Hawaii caused a VOG haze over the islands. There's trends in air quality. There's a graph here that shows levels of sulfur dioxide, nitrogen oxides, and volcanic organic compounds, or VOC, which I won't explain in depth. In 1970, there was a Clean Air Act establishing standards. Today, 5 primary pollutants and ozone are covered by the National Ambient Air Quality Standards. And there's a chart here that explains the standard values of each pollutant. And it shows the highest level that can be tolerated by humans without noticeable ill effects, minus a 10 to 50% margin for safety. And that's because different people can tolerate different levels of pollutants. So there needs to be a reduction of the level just in case there's a person who, just in case the person measured has a higher level of tolerance than somebody else who may be greater affected by a comparatively safe amount of the pollutant. So I won't read off the whole chart, but for example, carbon monoxide has an 8-hour average of 9 parts per million, and a 1-hour average of 35 parts per million. So the reason there are two different averages is because some chemicals you can tolerate them for a short amount of time, but not a long amount of time. So it factors in how much time you can tolerate at a certain parts per million. So in the case of carbon monoxide, you could tolerate a high amount of it comparatively. You could tolerate 35 parts per million for an hour. But you could not tolerate 35 parts per million for 8 hours. You could only tolerate 9. Air Quality Index. The Air Quality Index, the AQI, is a standardized indicator for reporting daily air quality to the general public. It provides information on what health effects people might experience within a few hours or days of breathing polluted air. Meteorological factors affecting air pollution. So there's a picture here of a factory creating pollution, and one picture has a wind speed of 5 degrees, or 5, I think that's miles a second, and the second one shows wind at 10, at a speed of 10. So in the 5 speed picture, the pollutants, the smog, is very dense, and it blocks out, it is hitting the neighboring city in the distance with a very thick, dark cloud. Where in the second picture, with a speed of 10, there's still a cloud hitting the city in the distance, but it's a little thinner, not as dense. Because the wind speed dilutes the pollutants and moves them, it spreads them out so that it isn't focused in one area. And it makes it a little more tolerable. The role of atmospheric stability. Atmospheric stability determines the extent to which vertical airflow will mix the pollution with cleaner air above. This correlates with what I was just explaining with the two pictures, the 5 wind speed and the 10 wind speed. The vertical distance between the Earth's surface and the height to which convection will carry pollution is called the mixing depth. The greater the mixing depth, the greater the air quality. Basically, you want pollution to spread out and dilute itself into the clean air. And the next few slides are going to explain what that means, the mixing depth, and how that works. So, stable versus unstable. When air is stable, convectional motions are suppressed and mixing depths are small. Instability promotes vertical air movements and greater mixing depths. This is where instability in the air is actually good because it moves the air around, spreads out the pollution a little more. This next slide shows inversions again and how that relates to pollution. So I'm going to read the text here. Many extensive and long-lived air pollution episodes are linked to temperature inversions that develop in association with the sinking air that characterizes centers of high air pressure. So there's two pictures here. One shows these factory funnels producing clouds, and at night there is a temperature inversion in this first picture, because basically two different temperatures of air are creating a barrier so that the air below does not go up into the atmosphere. But in the daytime, in the second picture, the air is able to rise up farther into the atmosphere, and this dilutes the amount of pollutants because it's able to rise up and out. So a higher mixing depth is when the air is able to rise up into the atmosphere and move around and dilute itself. And a lower mixing depth is when the pollution is trapped in a space at a certain height, and it's more condensed. Here's another picture. I'll read the text first. The turbulent surface zone does not subside as much. Thus, an inversion often forms between the lower turbulent zone and the subsiding layers above. Now, I missed a slide here. I missed the pictures in it. So the stable versus unstable slide has this little picture of a curve. And at the top of the curve is an unstable marker. At the bottom is a stable marker. And basically these are marking out where on this chart the mixing depth is. So unstable air will take the pollution up higher than stable air. And then there's also a neutral line where it's sort of a middle ground. It's not stable, it's not unstable, it's just neutral. And then the bottom picture shows how that relates to the clouds, with unstable clouds rising up higher than stable clouds, which are sinking down and stuck lower in the atmosphere. Serious pollution issues. There are two pictures here. The first one is a satellite image that shows high levels of aerosols associated with the October 2010 air pollution episode in China. And you can see that it has the aerosol index has a range from white to red, and it's very densely red here in this map, red and yellow. Then the second picture is a satellite image from October 8th, 2010, which shows the pollution. It looks almost like a big cloud, and it's actually pollution. Weather safety with pollution. To protect yourself on days with high particulate concentrations in the air, wear a surgical mask if you must be outdoors, wear reading glasses, not contact lenses, and use caution when driving. Acid precipitation. Rain is naturally acidic. It is slightly acidic. When carbon dioxide from the atmosphere is dissolved by a raindrop, it becomes weak carbonic acid. Small amounts of other naturally occurring acids also contribute to the acidity of precipitation. Effects of acid precipitation. Destruction to forests, plants, and roots because they can't always handle a high pH, high acid content. Wear on statues and monuments because especially metal doesn't react well to acid. Different materials don't react well to acid, and it wears down on them over time. It can discolor them, it can break them down. And then lake contamination. I think that's the last of my slides. I think that's the last slide. That was actually the last slide. I'm going to look real quick if I have any notes about acid precipitation. I do have one note here. Acid precipitation destroys forests, plants, and roots, wears on statues and monuments, particularly copper, and contaminates lakes. And the Northeast has a lot of acid rain due to industry. So that is all for Chapter 13 about pollutants. I will be doing Chapter 15 when it's ready. I don't have that yet. I'll do Chapter 15 as soon as that is in the Canvas. And I might start doing the earlier chapters, like Chapter 1, Chapter 2. They're more basic, but I think there's also things in there that could get forgotten because it's such a long time ago. So I'll try and read some other slides in the meantime. So thank you for listening. I hope this is helpful, and we're gonna do awesome. I know we are. So bye.